Okay, here we have a vertical problem again. And so let's get ourselves in that mindset. We are going to be using good problem solving and probably drawing a picture first. Read through the problem and see what picture would you draw. Can you identify all the knowns and unknowns and choose a good mathematical approach or the use of a graph? More and more, we're going to be using an equation. Try that for a few minutes, and when you get stuck, come back to the video. Pause it now. I am going to go ahead and draw a picture, like a realistic picture. Here's my ground level, and I'll make the argument that it doesn't really matter if it's ground level or not. The girl's going to throw a ball up in the air, and she's not going to have such a grotesquely long arm, but I think that looks about right. And here's the ball at the initial position. And it'll be perfectly fine if I call this level right here a y value equal to 0 meters. And yeah, I'm very comfortable ignoring the distance down to the ground or down to the roots of the tree and down to where, all of the goblins and demons live. Those things aren't relevant. Let's not talk about them. And here, she's going to throw the ball up to a maximum height, which is probably up here. And it does say that she's tossing the ball vertically, which I'd like to assume anyway. And the question is, how high will the ball rise above its height? And so, I realize I say and so a lot now that I'm recording these videos. This is the distance that we want to measure. And what should I call this? Delta x? Well, we're keeping delta x for the horizontal kind of stuff. So let's call it delta y. And it seems fine to agree that the up direction is the positive y direction. That's good because, as we've seen before, the downward direction is going to have a special relationship, a special kind of acceleration in the downward direction, right? What else do we know about this problem? We're not told anything about the time. Maybe that won't matter. And we do have to bring in that special action of things that happen with rocks and balls and, very, very small gold nuggets in the air, which is that they fly like they don't care at all about air resistance, which means that gravity pulls on them without any resistance, and the effect of that gravity is that they accelerate downward with an acceleration equal to negative 9.8 meters per second squared. And we give it a special name. We call it g as well. So g equals negative 9.8 meters per second squared. That is not given in the problem anywhere, but it is a given. We have to remember that. We have to not only remember it, but we have to remember to use it. Let me collect my thoughts for a little bit. I got excited. So I know the initial velocity, and I know the acceleration, and I want to figure out delta y. Okay, so I'm tired of just giving you the wrong equations. I think that this kind of equation would work out pretty well. The one that goes something like delta y equals the initial velocity times time plus 1/2 acceleration, which is g, t squared. And you'll see that this is written in the same format. In the text as your example as well. And conceptually, this is the part that is going up, right? Positive, positive. And then this is the part that's going down, because we have a positive squared and a negative. G is negative. And now I can be a little bit more clear. What do I mean by part that's going up and part that's going down? I suppose if you graphed this somehow, you could probably see like this as being like a part that's like above the line, and this as a part that's like below the line. But I'm just imagining that. Oh, let's remove all these little notes because I don't want them to be there permanently. Okay, forgotten. But what's not forgotten is this part's going to be negative. It's super easy to forget. I think that this is pretty straightforward. I think I'm ready just to plug some numbers in. Or, as they say in math classes, evaluate the relationship. Initial velocity is positive 13.1 meters per second. And the time, wait a second, we don't know the time at all. Okay. Going back for a moment. Looking at this equation, we know the initial velocity, we know g, but we don't know time, and we don't know displacement. This is starting to not look like a very good idea to use this equation. What other equations could we use? We could use delta y equals, I'm using black usually for this. Delta y equals 1/2 the average velocity. So velocity initial plus velocity final over 2 times time. Oh, there's time again. So like we know, we don't know. We want to use an equation that doesn't depend on time. And what is the only equation that doesn't depend on time? I think we're going to have to do it, y'all. I think we're going to have to do it. I don't want to use this. I don't want to use this. How about this? Velocity final squared plus, nope, not a plus. Equation number 4. Velocity final squared equals velocity initial squared plus 2 acceleration times delta y. I didn't want to do it. But we saw how equation number 3 and equation number 2 didn't work. And I think that this is most promising as well. So I'm glad we didn't start drawing graphs, I guess, because this one does not have a clear graphical interpretation. We know the final velocity. We'll have to talk about that. We know the initial velocity. We know the acceleration, and we don't know that. So that's a good approach. The final velocity at the top is 0. Where does it say that? Doesn't need to. How high will it rise? Well, it will rise, dot diagram, until it can rise no more. It slows down, and then it stops for a brief moment, for an infinitesimally small amount of time before it turns back around. That's how we know that this is given information as well. So in my process here, I'm reflecting, I did not stop to write down all the given information, and I may have caught that, but you need to be flexible enough to recognize additional facts when they come up. If I was to do this again and maybe have an extremely organized problem-solving strategy, I might have, almost like a table. Do I know time? No. Do I know delta y? No. Do I know initial velocity? Yes. Do I know final velocity? Yes. And do I know acceleration? Yes. And so I need the equation that cuts out time. Okay, let's solve it. But let's be humble. Hey, did you pause the video and did you get that? Because that's important. Don't blow it off. If you've watched this video and you didn't think about that, then you don't know how to solve these problems yet. You're just listening to me. Solving the equation. So we're going to solve for delta y. Do you mind if I do it like all at once? We've seen it before. It would be the difference of the squares. We get that by subtracting initial velocity from both sides. We divide both sides by 2 times the acceleration, and that is equal to delta y, or the vertical displacement. Final velocity goes to 0. Initial velocity is given, I'm sure, and we can start plugging in numbers, or we can evaluate it using the measurements. Negative v0 goes here, squared, divided by 2g, which itself is negative. Gosh, it's so easy to forget that. Initial velocity was 13.1 meters per second. Positive 13.1 meters per second. I already know that my units are going to end up being meters. I'm plugging, I'm not even putting the negatives in there because I see that they cancel. 13.1 squared divided by the quantity of, don't forget that. Force your calculator to be like, this is all in the bottom, divided by 2 times 9.8. Where's my meters per second squared button? And the displacement is evidently, gosh, what a weak throw. I don't know. 8.76 meters high. Okay. So I've solved it. I've written my solution. It seems pretty reasonable. Like, that's a little bit taller than a house. That's like about 27 feet or so. How high will it rise above its initial height? Cool. That's the whole answer. We did it. Sweet. I hope that you can start to see that sometimes using the equations, that is like the analytical relationships, is way easier than using a graph. I am trying to imagine where you would run into a problem using a graph, and I think it would force you to do something like really algebraic anyway. So hope you were able to work ahead of me and at least choose the right equation. Because if you could get to this far, then everything else falls into place. Everything else is like math skills. But finding the right equation requires a lot of physics knowledge. The hardest things I know from experience here are probably maybe remembering facts about gravity, which we treat as known information, interpreting the top of the motion as coming to a momentary standstill. Like, that's the hard stuff. Having an approach that leads you to a useful equation, eliminating not useful equations, is going to be what makes you successful in physics. Thanks for joining me. See you in class.